In this video, we're going to finish up section 9.3. We're still asking this question, when does a series converge? So we've got this infinite list of numbers, we're adding them all up, and depending on what that list of numbers looks like, our answer might be a finite number, or maybe it'll be some infinite number. And we've seen a couple examples now where adding up this infinite list of numbers gives us something finite. Let's now take a look at one where the series actually diverges. So the question, does the sum from n equals 1 to infinity of 1 over n converge? Well, the answer actually is no. And so we're going to see that in a couple ways. The first is we could just start calculating it. So recall that the partial sums are basically, say, start doing this series calculation. This series calculation would be 1 plus 1/2 plus 1/3 plus 1/4, etc. But the partial sums say start doing it, but then stop at this term. So the first partial sum says to stop after the first term. The second partial sum says to stop after the second term. Third partial sum, third term, etc. I actually want to write this one out. 1 plus 1/2 plus 1/3. Okay, and so these numbers are increasing. It's sort of tough to tell if they're going to like level off and maybe they don't ever get higher than 3 or something. So we could sort of jump ahead and try to find, all right, well, S10 ends up being 2.9. If we really jump ahead, S100 ends up being 5.2. 1,000 still keeps increasing. So these things are increasing at a decreasing rate. It takes us 900 steps to go from 5.2 to 7.5, but it's actually sort of still increasing. I'll put in one more, S10,000 ends up being 9.8. And starting to look at this sequence of partial sums, we might get an idea that, hey, maybe these numbers aren't going to level off. Maybe they're just going to keep going up forever. And that's actually what ends up happening here. The sum from n equals 1 to infinity of 1 over n ends up being infinitely large. So we're actually going to say that this thing diverges. What we have here is a graphic representation of the partial sum S3. In other words, we're talking about taking the first term plus the second term plus the third term of our overall sequence, of our overall series 1 over n. So this first term is represented graphically by a rectangle with width 1 and height 1. So this would be A1, this thing has area 1. The second term is represented by a rectangle with still width 1, but now height 1/2. So the whole thing has area 1/2. And then our third term has area 1/3. And what we want to point out, or the reason we're drawing it this way, is that we can compare this to the function 1 over x. So we typically use n's when we're talking about sequences in series, x's when we're talking about functions, but there's going to be some interchange between these two different ideas. We're adding up the series 1 over n and comparing that to the function 1 over x. So one thing we've talked a lot about in this class is the idea that the area under the curve, the area under 1 over x from 1 to 4 is the integral from 1 to 4 of that function dx. And the way we've drawn this here, we can see that this series, this partial sum, this part of the series is the left-hand approximation of the integral. So one thing that we've talked a lot about is that, well, this left-hand approximation is going to end up overestimating this. So this series ends up being bigger than the integral. All right, so we did this for the partial version. We could generalize that more and say that our Sn, which as we recall is the partial sum up to a certain n, our Sn is going to end up being bigger than the integral from 1, this ends up being n plus 1 of 1 over x dx. In other words, this series always ends up being bigger than the integral. We want to be careful and not say that the actual series going from 1 to infinity is bigger than the integral from 1 to infinity of 1 over x. When things are diverging and things are infinite, saying that one infinity is bigger than the other is a whole can of worms. But what we can say is that because this right-hand side approaches infinity as n goes to infinity, because this right-hand side diverges, so does the left-hand side, because the left at each step along the way, the left-hand side is bigger. So because of that, we can say that the sum from n equals 1 to infinity of 1 over n diverges. Cool. I want to make a very similar argument for this other series that looks very similar. The sum from n equals 1 to infinity of 1 over n squared. So we're going to do the exact same type of thing. We're going to put this on a graph, and we're going to say that, hey, these rectangles are going to represent how big, or the area of these rectangles are going to represent the terms that we're summing over, the terms in our series. We're setting this up a little bit differently. In our previous example, we said that the first term was to the right of 1. Here we're going to say that our first term, or our first term is to the left of 1, and this ends up being our second term, ends up having area 1/4. So we're setting up a little bit differently, but the same type of logic holds. We're going to compare the sum of the areas of a bunch of rectangles to the integral, or the area under the curve of some function on the similar range. So using that same logic before, we could say that the partial sums of this sequence, of this series, when our an is 1 over x squared, well, these partial sums are going to be less than the integral from 1 to n, and this ends up being just n rather than n plus 1, of 1 over x squared dx. And before, we were saying that, oh, hey, the right-hand side diverges, and the left-hand side is bigger, so it must also diverge. Now we're saying sort of the flip of that. We're saying that the right-hand side, if we remember that this integral ends up being some finite number, since the right-hand side converges, the left-hand side must converge as well. So because of that, this converges. And one thing I really want to emphasize is that, yes, this thing ends up being some finite number. This converges to a different number than the integral. Over here, we're using the right-hand approximation. We're going to be a little bit off. So this series is going to be a different value than the integral from 1 to infinity of 1 over x squared. But because the integral from 1 to infinity of x squared is a finite number, and this thing is less than that, this must also be a finite number. Okay, so that brings us to, that logic gives us what's called the integral test. And this is going to be one of our main tools for determining if a series converges or not. In other words, if we have a setup like this, and the key pieces here are if we have a series whose representative function is decreasing and positive, so both of these examples we are decreasing and positive, then we can apply this logic, compare this to the integral, and if the integral converges, so does the series, and if the integral diverges, so does the series. These things go hand in hand because we can use one argument or the other. When I mentioned the way that we set these up, the rectangles are bigger or smaller, depending on which argument we're trying to make, we can choose how we want to set it up. Okay, and I want to re-emphasize that in this case, when everything is converging, it is not the case, it's almost never the case that they're converging to the same number. Okay.